This is the last couple of problems from Chapter 12. There will be a few more review problems, but I think you should think of these as your sort of last hurrah with these problems. And what I mean by that is that at this point we've seen a good number of these problems, static equilibrium problems that is, and you should really give these a very strong effort before you go ahead and look at the videos. So just in case you haven't done that yet, I'd make sure you do that first. And also, if there's one little mistake here or there or something that you pick up on as you're going through the videos, then please do the right thing. Pause the video and try to correct your errors. Alright, that said, here's number 65. We've got a beam here and a cable attached to it here. This is 25 degrees, and I think this is 2 meters where that's attached, and the whole thing is 3.2 meters. The whole beam is 3.2 meters. I'm going to make a force diagram of the forces acting on the beam, and because they're not all acting at the same place, I will make it not a dot, but a beam-like thing. So there's that 2 meter point, and here's my tension force, and that's 25 degrees there, so this would be 65 degrees here. And then a little bit below that is the gravitational force, and I think they told me that the beam weighs 60 newtons. So that's the gravitational force. And there's also a force up here at the top of 50 newtons, an applied force. And then the hinge is a little bit tricky in this case. I think it's pretty obvious that the hinge will have an upward component here. I'm just going to make that small so it doesn't crash into this one. And then the other part, the y part of the force, I guess it's kind of hard to know exactly. You can guess which way it's going to go. But remember, if we guess wrong, we're just going to get a negative number for that. Now looking at this, looking at the tension force here, you can have some component here and this component. I'm going to guess that the force here would be this way. But because these are already two torques in opposite directions, it's really hard to know that. So if you guess the other way, or you weren't sure how to deal with that, you can make it either way, and if you guess wrong, you'll just get a negative number, and then you know that your arrow should have been going the other way. So I will proceed from here. So let's see. Oftentimes these problems yield to just doing the net torque equation, at least the first part does. So I'm going to go ahead and set that equation up. So in part A, I know that the net torque is 0. And that means that if I pick my axis to be here, which makes sense, it's going to knock out those two forces. And notice also that the gravitational force is anti-parallel to the radius at which it acts, so the torque from the gravitational force is 0. That torque right here is not trying to make the bar rotate either way. It's just pulling straight down like that. So that means this torque and this torque must be equal. This one trying to make it rotate this way, and this one trying to make it rotate the other way. So let's write our equations for those. So that means T, that force, times the radius at which it acts, that's 2 meters, times the sine of the angle in between. And that's important that you have sine 65 and not 25 there, is equal to 50. That's acting at the full radius of 3.2 meters, and that's acting at a 90-degree angle. So I'll write in sine of 90 here, but that's just going to be equal to 1. So those two torques have to be equal to each other. And somewhere around here is my calculator. So let's see if we can get that. Looks like one of my children is playing with my calculator. Look at that. That's funny. Woo! Crazy children. Look at that. FN int. Wow, they're doing some crazy stuff there. Let's get rid of that. Okay, so I got 50 times 3.2 times the sine of 90, which is 1, divided by 2 times the sine of 65. Let's make sure they didn't change to radian mode. They didn't. They don't really know what that means yet. They're only 6 and 4, so cut them a little slack there. So the tension force is about 88 newtons. And then for part B, I know that B, they want the, in unit vector notation, they want the force from the hinge. So that means we just want the components. Oh my goodness, look at those. I labeled those wrong. You probably have been screaming about that, haven't you? Because you know what X and Y mean. And so do I. Sorry about that. So X was the, sorry, on all that discussion there, X was the mystery one. I'm guessing that it's going that direction. We shall see. So let's do that first. I know that all the sum of those horizontal forces is 0. So let's see. That means in the x direction, the way that I have it written here, we'll see if this is right, I have Fx plus 50 newtons. Those are the forces in this direction, would be equal to T times, that would be the component opposite to the 65-degree angle. So that would be the sine of 65. So that would mean my horizontal hinge force would be 88 sine 65 minus 50. And it's a positive number, so I guessed right. That's about 30 newtons. And sum of all forces in the vertical direction is also 0. So let's see what we have there. I have in the up direction, I have just Fy. And in the down direction, I have 60 newtons from the gravitational force. And I also have the cosine component of the T force. So T cosine 65. And that's 60 plus 88 cosine 65. That's about 97 newtons. So in unit vector notation, my hinge force would be equal to 30I plus 97J newtons. 'Tis the hinge force. Right. So I hope that that type of problem is becoming fairly routine now. And just in case it isn't, here's another one. Number 78. Once again, static equilibrium. I've got a beam here, and there's a horizontal cable attached to it here. And let's see what we know. The beam has a length of 12 meters. It's supported by a horizontal cable and a hinge at an angle here. Angle theta is 50 degrees, which means that this is 40 degrees, by the way. Tension in the cable is 400 newtons. And they want to know in unit vector notation, what are the gravitational force on the beam and the force on the beam from the hinge. So same kind of thing, except this time we know the tension force, so we don't know the weight of the beam, so we're going to try to find that instead. But it's the same idea. So for part A, sum of all torques is 0. And I will choose this as the axis. And I guess I'm skipping the step of making the force diagram, which I should not skip. So let's do that. So if that's the beam, right smack in the middle, I would have the gravitational force, and I don't know what that is. I have the tension force causing a torque up here, 400 newtons, and that's 40 degrees there. That's the important angle for us. And then down here, the hinge, I have I'll try to get them right this time, y and x. So that's a similar diagram to things that we've done before. All right, so if this is my axis, for the purposes of calculating torque, then I have two torques. This torque here trying to make the beam rotate clockwise, and this one trying to make it rotate anti-clockwise. So that means that mg, oh, and I should write in here, let's see, I should put my angle in here just so I can be clear about it. If that's 50 degrees, these are alternate interior angles, so that's also 50. Also, you could say if that's 40, then that's 40, so that's got to be 50, but one way or another, that's a 50-degree angle there. So mg times the radius that it's acting at halfway, that'd be 6, times the sine of 50 degrees. And then torquing the other way, I have the tension force times the full length of the beam it's acting at, 12 meters, times the sine of 40 degrees. And those two have to be equal to each other. So do they want the weight or do they want the mass of the beam? They want the gravitational force on the beam, so I'm just solving for mg here. We could, of course, find the mass easily there by dividing by 9.8. That's not what they asked us to do. So 400 times 12 times the sine of 40 divided by 6 sine 50. That looks like about 670 newtons. That's part A. And then in part B, do the same thing. Oh, and they wanted actually just to be consistent with what the book is asking for. They said in unit vector notation. So the gravitational force here is straight down, so that would be negative 670 J newtons. Right, that's what they asked for. So. And in part B, again, we're going to do it, our final answer will be in unit vector notation. My horizontal forces are balanced, and those horizontal forces are this and this. So, well, that's easy. So Fx just has to equal 400 newtons. Right? There's no other components there. And likewise, I think this one's just as easy. Also balanced in the vertical direction, and my only vertical forces here are Fy and the gravitational force, which is 670 newtons. So that means the hinge force in unit vector notation is 400I plus 670J newtons. And that's it.